Today we're going to talk about Le Chatelier's principle. This is one of the main ideas in equilibrium. Le Chatelier is a Frenchman. Make sure we're giving it the proper enunciation here. We're not going to say Le Chatelier. Le Chatelier. So with Le Chatelier's principle, you're going to be able to predict what changes will occur when a system that is at equilibrium is disturbed, and you'll be able to suggest how to reestablish equilibrium. So equilibrium position is dependent upon four things. So we have the temperature, the volume of the container, the concentration of either your aqueous substance or your gaseous substance. So if you have a solid or a pure liquid, that's not going to change us with Le Chatelier's principle, and pressure. So the position of a chemical reaction is said to lie to the left if the reaction favors the reactants, or lie to the right if it favors the products. So when a change happens to a system at equilibrium, the position of the equilibrium shifts in a direction to reduce the effect of the change. So let's think of this in your perspective for a minute. Let's say you're stressed. If you're stressed, there's something that you do to compensate for that. Some people maybe go for a run, or some people maybe read a book. There's lots of things that you can do to compensate to reduce your stress level. The equilibrium in a chemical reaction, the equilibrium is going to do the exact same thing. It's going to do something to minimize the effect of the stress that is applied to the system. So the first thing that we have is the effect of a concentration change. So our K is going to remain constant. If we add a product, a reactant or a product, the system's going to shift away from it. So add and away both start with the letter A, so you can use that to kind of help you remember that. If you remove a reactant or product, the system's going to shift towards it. So this is all the system trying to compensate for the change that's imposed on it. Let's look at an example. Here we have the reaction to produce ammonia. This was a very popular reaction that this is commonly used because this is a very inefficient reaction. This is the reaction that was actually used that Le Chatelier was using in order to come up with his theory. So we have nitrogen and hydrogen gas trying to make ammonia. This reaction is very difficult, so we try to do things to help it. So one of the ways that you can kind of visualize this is by thinking of kind of a balancing act. So right now, our system is at equilibrium, so our reactant rate and product rate production are equal to each other. So we're at equilibrium. But we're going to stress the system, and in this case, we're going to stress the system by adding N2 gas to it. So N2 gas is a reactant, so we're adding a reactant, so it's going to shift away. Another way to think of this with this kind of balancing act is we're adding a reactant, so the balance is going to go down on the reactant side, and the product side is going to now go up. So this is what we did, so we have to figure out how we're going to compensate for this. So in order to compensate for this, we're going to shift right towards the products. So when we do that shifting, we're going to then have an equal balance on each side. So the reaction shifts towards the right, towards the products, to balance the equilibrium. So let's take a look at another stress on the system. So let's add NH3. So this is a product. What's going to happen to our balance beam? We're adding a product, so the product is going to go down. So in order to restore equilibrium, we're going to have to shift to the left towards the reactants. So when we do this shifting to the left, we're producing more reactants, then causing the equilibrium to be restored and be balanced. Okay. What happens if we remove NH3? So remove, we're going to shift towards it. It's a way to remember it. Or if we think of the balance beam here, we're removing a product. So if we remove something from the balance beam, that side's going to go up. And we're then going to shift to the right towards the products to restore equilibrium. So let's take a look at another reaction. So we have calcium carbonate producing calcium oxide and carbon dioxide. So the system's at equilibrium. We're going to remove some CO2. So we're at equilibrium. We're going to remove some CO2. So the product side is going to then go up of my balancing act. In order to restore equilibrium, I'm going to shift to the right to produce more products. When I produce more products, my equilibrium is then restored. Let's take a look at another example. Adding CaO. Now, we have our equilibrium here. CaO is a product. However, notice CaO is a solid. Since it is a solid, it's going to have no effect on equilibrium. In order for this to have an effect, if we're in a solution, the solid has to be able to be dissolved. If we're not in a solution, solids will never have an effect. So in this reaction, we only have solids and a gas. We have no solution whatsoever. So we have CaCO3. We add it. It is a reactant. However, again, it's a solid. It's going to have no effect. So we're going to take a look now at the effect of changing pressure. So when we change pressure, K is remaining constant. If we add or remove a gas reactant or product, it's going to be the same as concentration. So if we add a gaseous product, it's just like increasing the concentration. If we add an inert gas, so examples, these are like the noble gases like helium, argon, nitrogen gas. Gases that are not going to be involved in the reaction, that are unreactive, are not going to change the system either. What about the effect of changing volume? So both concentration and partial pressure of the substances are going to change. This is the one that's a little bit tricky. So when the volume decreases, the system responds by decreasing the total number of molecules. The reaction system will respond by shifting to the side with the least number of gas molecules. When the volume increases, it's going to shift to the side with the most molecules, more space available, naturally taking up that space. Other thing to keep in mind here, we want to make sure we're thinking of this in terms of pressure as well, thinking back to the gas unit. So if we decrease the volume, the effect is going to be the pressure is increased. So because of that increased pressure, the system's going to respond to try to shift to the side with the least number of gas molecules. So sometimes pressure is referred to instead of volume. So let's take a look at an example here. So we have nitrogen gas. We have our same reaction here. The first thing we want to do is we want to decrease the volume of the container. So on the reactant side, we have 4 particles. So we have 1 nitrogen and 3 hydrogens. On the product side, we only have 2 particles. So if we decrease the volume, we're going to shift to the side with the least number of particles, which in this case is the products. We're going to shift towards the products because we're trying to compensate for our decreased volume, which results in an increased pressure. And then increasing the volume has the opposite effect. We're going to shift left towards the reactants. So I know this one's kind of hard to think of, so I have another visual here. So, So here I have kind of a made-up reaction. We have stars and hearts. Our stars are A, which is our reactant. The hearts are B, which are our products. So if we are decreasing the volume, which increases the pressure, what's going to happen is we're going to shift towards the product side here because we have less products. So we're shifting to the products in order to produce or just kind of save this a little bit of space. So are these proportions exactly perfect? No, it depends on the reaction and other factors. This is just a visual to help you illustrate what's happening. So if we compare this to the last reaction, the stars would be like the nitrogen and the hydrogens. The hearts would be the ammonia, excuse me. So here we are doing the opposite. We're increasing the volume, which results in a decrease in pressure. So initially we have 5 smiley faces, which represent the reactants, and 15 products, which represent triangles. So when we increase the volume and decrease the pressure, we have less smiley faces, we only have 3, and more triangles. So we're shifting to the side that's going to try to fill up that space. Thinking about it in terms of a chemical reaction, in this reaction we have solids and gases. So on the product side we have solids only, so there's 0 gas particles. On the product side we have 1 gas particle, the carbon dioxide. So if we decrease the volume of the container, we're going to shift left towards the reactants. Why? Because there's less gases over there. So we're shifting to that side. If we increase the volume of the container, we're going to shift right towards the products to try to fill the space. So the last one, last effect is the change on temperature. The effect of changing temperature, K changes with temperature changes. So we want to treat delta H, which is what's going to be provided to you, as a reactant or a product being added or released as the temperature change. So an endothermic reaction means energy is being absorbed, so we have a positive value. An exothermic means energy is being released, so we have a negative value. So the positive value we're going to add to the reactant side. The negative value we're going to add to the product side. So once we figure out what side, we can treat it just like adding or removing a product. So let's take a look at an example. So we have our ammonia reaction. We have that plus 92 wasn't supposed to be there. So we were given that delta H is negative 92. Since it's a negative 92, we know it's an exothermic reaction and energy is going to be released. Because of that, we're putting the plus 92 on the product side. Once we have that on the product side, we are then disturbing equilibrium, or we're stressing the system. The first thing we're doing is increasing the temperature. So increasing the temperature is like adding energy. So that's going to cause it to shift away. So it's going to shift to the left towards the reactants. So the first thing we're looking at increasing the temperature of this reaction. We have the delta H is negative 92. So we're going to add the energy to the product side because it's a negative. So increasing temperature is like adding energy. So in this case, we're adding energy to the product side, so we're going to shift away. So we are starting off with a balanced rate. We're adding a product, so we're going to need to shift towards the reactants in order to make up for this loss, or for this change. So when we shift left, we then restore equilibrium. For the next one, we're going to decrease temperature. Again, we have the positive 92 on the product side because we have a negative 92 as our delta H. So then we have our balancing act. In this case, decreasing temperature is like removing heat. So we're going to shift. So we're removing a product, so we're going to shift to the right in order to restore equilibrium. So we have another reaction here. We're going to increase the temperature. So we have a positive 198 delta H here. So that's going to be like it's a reactant. So we have it on the reactant side. So when we increase temperature, it's like adding a reactant. So we need to shift to the right towards the products in order to compensate for this. And then decreased temperature, we still have an endothermic reaction. The delta H is positive, so it's going to be on the reactant side. We're decreasing the temperature, which is like removing a reactant, so we're going to shift towards the reactants in order to compensate and restore equilibrium. So just thinking about this in terms of K, so for an exothermic reaction, if the temperature increases, the K is going to decrease. If the temperature decreases, the K is going to increase. For an endothermic reaction, if the temperature increases, K will increase. If temperature decreases, it'll decrease. So remember, K is indicating what's happening in the reaction. The larger the K, the more likely it's going towards the product side, or it favors the products. Larger Ks proceed towards